Hello, welcome to my project on the visualization of continual backpropagation. One of the biggest challenges in deep learning is something called catastrophic forgetting. When you train a neural network on new tasks, it tends to overwrite what it learned before. The network forgets. Recently, I came across a paper on continual backpropagation, an approach that tackles this by selectively reinitializing low-utility neurons during training. Instead of letting dead neurons sit there wasting capacity, the algorithm replaces them with fresh ones. What caught my attention was that networks using this method showed significantly less performance drop-off when transferring to new material. That got me interested. I shifted my research focus to continual learning, and I wanted to understand what's actually happening inside the network when these neurons get replaced. Not just the numbers, I wanted to see it. So I built a real-time 3D visualization of a continual backpropagation neural network as it trains. Here's the visualization. We're looking at two neural networks side by side, an actor network on the left and a critic network on the right. This is a reinforcement learning setup trained on a mini-grid environment. Each sphere represents a neuron. The input layer is at the bottom, the hidden layer in the middle, and the output layer at the top. The actor has 16 hidden neurons and 7 output neurons, one for each possible action. The critic has 16 hidden neurons and a single output for value estimation. The size of each neuron tells you its utility, how useful that neuron is to the network right now. A large neuron is pulling its weight. A small one is contributing very little and is a candidate for replacement. So what is this network actually being trained on? It's a mini-grid environment, specifically the door key task. The agent has to navigate a grid, pick up a key, unlock a door, and reach the goal. I started training on the 5x5 version, which is small enough for the network to learn fairly quickly. Then I moved to 6x6 and finally 8x8. What's interesting is that the network could not learn the 8x8 environment if I started there from scratch. But by building up through the smaller grids first, 5x5, then 6x6, then 8x8, it was able to transfer what it had learned and succeed. This is exactly the kind of thing that drew me to continual learning in the first place. The continual backprop algorithm is recycling low-utility neurons and making room for new features. And that seems to help the network adapt as the task complexity increases. Being able to visualize what's happening inside the network during this curriculum progression is the whole point of this project. The connections between neurons are rendered as smooth Bezier curves using a custom geometry shader. Every visual property encodes information. Color tells you the sign of the weight. Green edges are excitatory, positive weights that amplify the signal. Red edges are inhibitory, negative weights that suppress it. The thickness maps to the magnitude of the weight. A thick edge means a strong connection. A thin edge means the weight is close to zero. Curvature also reflects magnitude. Stronger weights curve more, and the direction of the curves tells you the sign. Positive weights curve one way, and negative weights curve the other. Finally, the transparency of each edge is tied to the utility of its source neuron. Low-utility neurons have a faded connection, so you can visually identify which parts of the network are becoming irrelevant. You'll notice some neurons have a bright cyan glow around them. That's a volumetric halo rendered with a custom shader, and it represents the neuron age. When a neuron is freshly initialized, either at the start of training or after being replaced by the continual backprop algorithm, it glows brightly. As the neuron ages and matures, the glow fades away. After about 100 training steps, the halo is gone entirely. And when a neuron actually gets replaced, you see a particle burst, a ring of particles expanding outward from that neuron. This makes it easy to spot reinitializations in real time as you scrub through the training data. Watching the network train frame by frame, a few things stood out to me. First, you can clearly see that not all neurons are equal. Some hidden neurons grow large early and stay large. They've found useful features and they keep them. Others shrink down and eventually get replaced. The continual backprop algorithm is essentially performing a kind of natural selection on neurons. Second, when a new neuron is initialized, you can watch its connections rapidly adjust. The edges shift from thin and faded to thicker and more saturated as the neuron finds its role in the network. It's almost like watching a new employee get up to speed. Third, the weight structure between actor and critic evolves differently. The critic network, with its single output, tends to develop more uniform connection patterns. The actor, with 7 outputs competing for the hidden layer's attention, shows more specialization. Certain hidden neurons become dedicated to specific actions. These are the kinds of patterns that are hard to pick up from loss curves alone. Seeing the structure change in 3D gives you an intuition for how the network is learning, not just that it's learning. This project started as a way to build intuition about continual backpropagation, and it's already shaped how I think about my research. Being able to see which neurons survive, which get replaced, and how the weight structure reorganizes, that's given me concrete ideas for what to investigate next. My broader goal is to improve general neural network performance through continual learning techniques. This visualization is one tool in that effort, a way to look inside the black box and actually understand what the algorithm is doing. If you're interested in continual learning or neural network visualization, please feel free to leave a comment or reach out. Thanks for watching.